Lesson 123 is called Numerals and Numbers, and it finishes on real numbers and the different subsets of real numbers. To begin with, I think this is review the idea of what a number is versus what a numeral is. If I've got, let's say, some marbles, and I've got 3 out on the table, a number is an idea that we use to count. So if I have 3 marbles sitting on a table, they represent the quality of threeness. I mean, there's this idea that you can count to 3, and there are 3 here. If it's pencils, it doesn't make a difference. I have 3 pencils. I have what's called 6. We've invented a word for the idea of what you can count 1 to 6, what you see here. Now, when I want to show that idea in what we are familiar with as numbers, they're actually called numerals. So numbers are ideas, and a numeral is the symbol we write to make us think of the idea. It's the symbol. So count it up and you get 3, write it down, and you'll write the number 3, right? A symbol is something we write down to represent this idea of 1, 2, 3. It's not a number, but is a numeral that makes us think of the number 3. The ancient Romans used their own symbol that we'd call a numeral. It was a Roman numeral. Okay? That's not a number. This isn't a number. The number 3 really is a symbol, a numeral 3. And we can show 3 as 30 over 10 is called a numerical expression with a value that goes back to 3. Its value is 3. So we're not changing its value. Not really even changing the number. We're just changing the way the numeral is written. That's helpful when you think about adding up fractions. 1/4 plus 1/2 can totally be added up quickly if you have them drawn out for you, because then you've got the idea right there, and you can add ideas easily. You can add half a pencil to a fourth of a pencil to see that I have 3/4 of a pencil. But when you're working with numerals, you got to make the numerals match, and so we change this so that its denominator is 4. We've changed the numeral, but the number, the idea is still the same. It's just changing this denominator so we can count the same to get to that 3/4. This is all written out beautifully on page 392. Now, the subsets of real numbers. Real numbers are like everything. Anything we've worked with, even irrationals, are called the real numbers. This graph, I'll give it to you, is helpful, I think, in visualizing. And notice, if I asked which subsets of numbers, the subsets are all the titles you see shown here, which subsets of numbers are contained by the title real numbers? And looking at this chart, or the chart on page 393 that looks different, it's just more square, we see that everything is contained by the title real numbers. They're all within the pool of blue. Therefore, anything is inside that one. That's the largest category. It'd be like saying, which shapes are called shapes? All of them are called shapes. But then you start saying things like, which shapes are quadrilaterals? Now you're down to squares, rectangles, rhombus. Not everything is contained by that. So let's think of that as our next one down. Rational numbers contain most other numbers, but not all of them. Which numbers? Types of numbers, subsets, we call them. Subsets of the real numbers are not rational numbers. Ding, 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 ding. Irrational. What's the difference? The natural or counting numbers down here are the 1, 2, 3, 4, 5. It's the smallest subset. It starts at 1. They're only positive integers. 1, 2, 3, 4, so on. Whole numbers are not enough if we wish to express fractional quantities. Remember, whole numbers include 0, 1, 2, same then after that. But integers are where we're allowed to start using negatives, -5, -4, and so on. And then rational numbers are where we can use fractions, everything between 1 and 2, and so on. Anything we want that is less than 1 or parts of 1. 5.5 or 11 over 2 is a rational number. But some numbers cannot be expressed as integer over integer like we've been showing, 11 over 2 and so on. And these are the strange numbers we call the irrational numbers. Irrational numbers cannot be expressed as a ratio of integers. To express no quantity, or sorry, scratch that last part, but an irrational number cannot be shown. The most common one is pi because it goes on forever. It can't be shown as a perfect integer over an integer. Other examples are square roots that don't come out, like a cube root of 5 goes on forever, or not forever, but it cannot be shown as an integer over an integer. Negative square root of 2. There's a bunch of examples on page 493. These are the irrational numbers. They don't count as rational. They're their own category. They're the only subset of real numbers that are not rational. Within the rationals, you have integers, whole numbers, and natural numbers. If I ask you, here's my last question for you. To which number sets does -3 belong? Which would you say? Does it belong to the natural 1, 2, 3s? No. Why? What's wrong with 1, 2, 3s? It doesn't contain negative. They're only positive integers. What about whole numbers? -3. Nope, starts at 0. Again, doesn't contain negative numbers. Integers, yes. So integers, it's a member of the integers. What about the rational numbers? You might say, I see -3. Doesn't look like a fraction. It's not rational like we said with the, but it is, right? Because it's technically what? -3 over what denominator? 1. If it's contained by rational numbers, it must be within the rational numbers too, even though we think integers when we think -3. So rational, and then what's the last one? That's always the set. Always the real numbers, which you can abbreviate that way. It's an R with 2 vertical lines. Sorry if I cut any of this off. I just realized I'm too far to the right. Integers, I showed abbreviate real numbers like that. Okay, let me know if you have any questions. Try the one practice problem assignment for next time.